Good evening. Today we are going into our next session in that chapter ray optics. We start with thin lens formula. Thin lens formula you've learned in 10th standard. 1 by V minus 1 by U equal to 1 by F. Also in the previous session, just after the lens maker's formula, the last formula that we arrived at is the thin lens formula. So you can be asked to derive the thin lens formula from lens makers, or you may ask to arrive at that thin lens formula from the ray diagram. So we have learned all the ray diagrams in class 10. So you need to know all of those ray diagrams. Here I've taken a ray diagram where we've kept the object between the focus and the center of curvature, F and 2F. One ray parallel to the principal axis passing through focus, the other ray passing through the optic center, meeting after 2F, beyond 2F. The distance of the object from the optic center measured as U. From the optic center to the focal length is, focus is the focal length, and from the optic center to the image I have taken V, and you see it is an inverted, real and enlarged image. So using this ray diagram, we are going to arrive at the thin lens formula. Now first what we are going to look at is the two triangles here. That is, we have a triangle A-B-F and OMF. These two triangles are actually similar triangles because we have a 90-degree angle here. We have vertically opposite angles here, AA theorem, and we may take the proportionality. So since triangles A-B-F and OMF are similar, we may write similar triangles, and so we may write A-B- by OM equal to, so I have taken A-B- by OM. Now I am taking the base of the two triangles will be so this will be A-F by OF. Now our final formula, we need it in terms of U, V and F, right? 1 by F equal to 1 by V minus 1 by U. So we need to make sure that the right hand side, all measurements start from the optic center. So I need to change this AF as A-F. I can write A-F as OA- minus OF. So I'm going to rewrite A-F as OA- minus OF by OF. And on the left hand side, I'm going to make it A-B- by. You will see this OM is the same height as AB. So I'm going to rewrite this as AB, and that's going to be my first equation. Then in the next, to get my next equation, I'm going to take the two triangles that are common with the optic center. A-B-O and ABO are again similar triangles. You have a 90-degree here, then there are vertically opposite angles here. So I may write triangles A-B-O and ABO are similar. So then I may write proportionality as A-B- by AB. The base will be OA- and this will be OA. So I may write OA- and this is OA, which is my second equation. Now if you look at the first and the second equation, the left hand sides are the same. So I may equal the right hand sides and write OA- by OA must be equal to OA- minus OF by OF. Now I'm going to simply substitute for the values in terms of UVF. Now in 10th standard you've learned that the direction of incident light is taken to be the positive direction. So the incident light is towards the right, so we will take all measurements to the right as positive and to the left as negative. So here OA-, I'm measuring from O to the right, A- is V plus V by OA. So from O to the left, I am measuring OA, that is minus U, should be equal to OA-, that is V. Then OF is from O to the right, that is the focal length. So minus F by OF is F. I'll cross multiply. So this is VF equal to minus U into V minus UV, and minus into minus will give you plus UF. And if I divide throughout by UVF, this will be 1 by U equal to minus 1 by F plus 1 by V, or I may rewrite this equation, rearrange it and write 1 by f is equal to 1 by v minus 1 by u. And this is thin lens formula. Okay. So this is how you will arrive at the thin lens formula from ray diagram. Also, to get the magnification, you will look at this equation 2. Magnification, for magnification. From this equation, you may write from equation 2, this a dash b dash is the height of the image which is inverted. So minus hi by AB is the height of the object, erect. So HO is equal to OA dash is plus V by OA is minus U. Or magnification, as you know, is HI by HO, which is equal to V by U. So you need to arrive at the thin lens formula and the magnification of lens using ray diagram. Okay. After this, we go on to the power of a lens, which I'm sure you know already from 10th standard again, defined as the reciprocal of the focal length of a lens is defined as the power of the lens. So the same thing, but in a slightly different manner, we need to arrive at that definition when you are in 12th standard. So what we do here is, we have a lens here. So we have, suppose we have a lens, a convex lens, converging lens. If you take a parallel ray incident at a height h, you know, because it's a parallel ray, parallel to the principal axis, after refraction it must pass through the focus. Okay, so this happens to be the focal length. Now let's take this angle as delta, so that tan delta is going to be opposite side, that is h, by adjacent side, that's the focal length. Now if you take this h to be equal to 1 meter, we may write tan delta is equal to 1 by f, which is defined as the power of the lens. So in words, if you're going to put this, you will define power of a lens as a tangent of the angle through which a lens converges a ray parallel to the principal axis incident at 1 meter from the optic center. If you were talking about a concave lens, this would have diverged. This ray would have been diverged, and you will see that the tan delta will be here. So you will define power as the tangent of the angle through which a concave lens diverges a ray parallel to the principal axis incident at 1 meter from the optic center. Okay, and you know this SI unit of power is diopter, and this is 1 diopter is 1 meter raised to minus 1. So when you 1 by f is power, so focal length has to be in meters when the SI unit of power is in diopter. The next thing that we need to derive here is, what will be the total focal length of many lenses in combination when they are kept in contact with each other. Okay, so here we will just deal with 2 lenses, but the same goes for any number of lenses that you use. So we are going to derive focal length of combination of 2 thin lenses in contact. So you're keeping 2 thin lenses in contact. So that is, we have one lens here and another lens in contact with that. Okay, let me call this as the first one and this as the second one, and let me take this as the principal axis. Now because they are thin lenses, we may approximately take the optic center to be here. Now if I have an object here, this ray of light incident on the first lens, had this lens not been there, if this weren't there, would have now formed an image at I1, right? So for this, so that means would have formed at I1. Okay, fine. Now if you keep one more lens here in contact, then what happens is this ray cannot go on to form this image here, because this ray will now have to undergo one more bending because it is passing from a denser to a rarer medium, and because your normal is like this ray will bend away from the normal and get the final image at I. Now what is to be understood is, for the first lens, its object is here. If this had not been there, its image would have gone on to I1. So if I take this as U and this as V1, for lens 1 I may write 1 by focal length of the first one equal to 1 by V1 minus 1 by U, my first equation. Right. Now for the second lens, this cannot be the object because the ray has already undergone bending, refraction. So this is the incident ray that we are talking about for the second lens. So that is here, that's actually this one. So the image formed by the first lens is now acting as the object for the second lens, right? Such an object is what I have told you earlier, is called the virtual object. I repeat, the image formed by the first lens is now acting as the object for the second lens. Such an object is what you call as a virtual object. So for the second lens, this is the object, the virtual object for second lens, for lens 2, and this will be the final image, the image of the second lens. So for lens 2, when I write the thin lens formula, 1 by f2 is equal to 1 by v, which is the image distance. This one is the image distance v of the second one, minus object distance will be 1 by v1, equation 2. Now if I add the two equations, I have on the left hand side 1 by f1 plus 1 by f2 equal to this 1 by v1 and minus 1 by v1 get cancelled, and you have 1 by v minus 1 by u. So 1 by v minus 1 by u. Now you will see that the combination object is lying at a distance u, final image is lying at a distance v. So this 1 by v minus 1 by u must be the focal length, 1 by f of the combination. So you may write 1 by f is equal to 1 by f1 plus 1 by f2, or this is the power of the combination equal to p1 plus p2. Now we have derived this final formula for two thin lenses in contact, convex, but the same goes for any number of lenses. If you have 3, then p equal to p1 plus p2 plus p3 and so on. You can have all concave lenses, or you can have a combination of convex and concave, no problem. Only thing is, if it's a convex lens, you will take the focal length as positive. If it's a concave lens, you will take the focal length as negative. Okay. Now after this, we go on to the prism formula. Prism formula. Okay. Prism formula. So we have a prism here. This angle is called the angle A of the prism. This is a base. I am drawing the normal to both sides. And this is the incident ray, which makes an angle of incidence, the angle between the incident ray and the normal. And the incident ray I am going to call PQ, right? And this ray would have continued in its path, original path, had it not have to. Now this ray is passing from rarer to denser, so it can't continue in its path like this. Instead, it will have to bend towards the normal, because it is passing from rarer to denser. So instead of going on like this, it will bend towards the normal, and this will be the refracted ray. And now this ray, which is incident here, makes an angle of incidence here. So it has to now pass from denser to rarer. So instead of continuing in its path, it will bend away from the normal, and this is called the emergent ray QR, making an angle of emergence. Now I am going to call this angle as R1 and this as R2, and this, if I extend it back here, this angle is called the angle of deviation. delta, because how much has the incident ray deviated before coming out of the prism. That angle is what you call as the angle of deviation. I'm going to call this as n and this as m. Right? So first we are going to look at the quadrilateral. From the quadrilateral, A, Q, N, R. You see this quadrilateral A, Q, N and this is RS. So we have A, Q, N, R as a quadrilateral. Now for this quadrilateral, you know this is a 90, this is also a 90 because this was a normal, right? So this angle and this angle are 90 degree. So this 90 plus this 90 is 180. So remaining angle A plus angle N must be the remaining 180 because total sum of angles for quadrilateral is 360. So I may write angle A plus angle N equal to 180 degree, which is my first equation. Then I am going to look at the triangle. From the triangle QNR, that is this triangle QNR, angle sum property says R1 plus R2 plus this angle N must be 180. So I am going to write that R1 plus R2 plus the angle N is that 180 degree. Equation 2. If I look at the two equations here, you will see that this N is common, 180 common, so which means angle A must be equal to R1 plus R2, which I will take as my third equation. Next I am going to look at the triangle QMR. Triangle QMR, that is this one, QM and R. You know that this is the exterior angle, should be equal to the interior opposite angles. So this delta must be equal to this plus this. So I may write exterior angle delta equal to, now see, this whole angle is angle I, vertically opposite. So this should be full I minus R1. So I may write I minus R1 plus, now this whole angle here, this much, this whole angle is equal to this angle because they are vertically opposite. So this portion will be equal to total E minus the R2 will be here. So I may write E minus R2, or I may combine this and write I plus E minus R1 plus R2 as my fourth equation. Now we have got the four equations. Okay. Now here you will see that if you are going to draw a graph where you have delta here and angle I here, you will see that you are going to get a graph like this, where this is called the angle of minimum deviation for some corresponding and for some angle I. Minimum, the delta will decrease, reach a minimum value D and then increase back, right? Now this is because, see, you will have two corresponding values, because if you see in your equation, delta will be the same for two values of I, because if you interchange this, you will have the, see, let's for example, I is 20 and E is 40, okay? Then you have a particular delta. If I interchange for I 40, then E will become 20 and you will have the same value of delta. So delta will be, two values will be the same, same delta for two values of I. That's why your graph will look like this, and this is the minimum value of delta, that is angle of deviation, called the angle of minimum deviation. Now I am going to, so here at this particular condition here, when delta is equal to minimum value D, you will see that I becomes equal to E and R1 becomes equal to R2. For that particular position, this ray QR will be parallel to the base. That means R1 and R2 will be the same and I and E will be the same for this minimum condition, that is when angle of deviation is equal to capital D. I am going to substitute those values here in my equation 3 and 4. Okay. So we now take the equation 3 and 4, and I'm going to substitute these conditions that we discussed just now. That is, if when delta is equal to capital D, we know R1 and R2 are the same. So A will become equal to 2R. I'm taking R1 equal to R2. Let me write that. R1 is equal to R2 is equal to R. So angle A will become equal to 2R. Or I may write R is equal to A by 2. Then if I substitute the same thing in the next equation, that is my fourth equation here, this delta will become what? D. This is equal to I and E are the same, I said. So I plus I will give you 2I minus R1 plus R2 we know is A. We know from our equation A equal to R1 plus R2. So I may write this as I equal to A plus D by 2. Right? 2I is A plus D and I will be A plus D by 2. I am going to write Snell's law. Snell's law, which tells you N21 is equal to sin I by sin R. Sin I we know is A plus D by 2. So I'll rewrite that as A plus D by 2 by sin R. Sin R is A by 2. A by 2, and this is what you have as prism formula. Remember, we said that, see, ray of light is passing from rarer to denser. So this is the first medium, this is the second medium. So when you write N21, it is actually refractive index of the denser medium with respect to rarer medium equal to sin A plus D by 2 by sin A by 2. This A is the angle of prism, D is the angle of minimum deviation. This delta will take a minimum value when called D, when I and D will be the same and R1 and R2 also will become same. By A by 2, this is called prism formula. Okay. So, and in case you have thin prisms, suppose you have thin prisms, you may rewrite the formula or modify the formula to for small angles, you know sin theta is equal to theta. So you may approximately say sin A plus D by 2 for small thin prisms. When angle A is very small, you may write sin A plus D by 2 as A plus D by 2 and sin A by 2 as A by 2 because sin theta is equal to theta. So we may write NdR is equal to A plus D by 2 by A by 2, or you may write D is equal to N21 minus 1 into A, where this is denser with respect to rarer. So these are the things that we discussed today. We started our class with lens formula, that is 1 by V minus 1 by U equal to 1 by F. We went on to define power, then power of a combination of lenses, and then last what we have here is prism formula. So thank you and good night.